begins the Chapter 10 video lessons, Molecular Approach to Chemistry, where the focus is on bonding. Chapter 9, of course, dealt with Part 1, which was a review topic from last semester. Chapter 10 starts chemical bonding and really getting into more about molecular shape. Let's go ahead and take a peek at our first slide. It says structure determines properties. Properties of molecular substances depend upon the structure of the molecule. We see that the structure includes many factors, such as the skeletal arrangement of the atoms, which simply means what's bonded to what, kind of getting a three-dimensional look at how atoms are connected together. The kind of bonding between atoms lends itself to properties. Ionic, of course, being metal to nonmetal. Covalent is a nonmetal to nonmetal, and the term polar covalent, that unequal sharing of electrons. Of course, the shape of the molecule also is important in determining the chemical properties. So the bonding theory should allow us to predict the shapes of molecules, and that's really the focus of this particular chapter. So much of molecular geometry depends upon the chemistry of our molecules. So when we think about molecular geometry, it really is just giving us a three-dimensional look at the structure of atoms, a three-dimensional look. So it describes the shape of a molecule, which really relates to its geometric figure. The geometric figures have characteristic corners that indicate the position of the surrounding atoms. The surrounding atoms always attach back to the central atom in the center of the geometric figure. That geometric figure will also have characteristic angles that we call bond angles. So thinking about how the atoms are connected in a three-dimensional way, and then taking a look at the angles between the atoms that attach back to the central atom. Now the Lewis theory of bonding, or the electron dot structure, also known as Lewis dot structure, predicts that there are regions of electrons in an atom. So some regions result from placing shared pairs of valence electrons between bonding nuclei. Other regions result from unshared valence electrons in a single nuclei. So just to illustrate, if we think about a water molecule, oxygen being the central atom, we know that there's two unbonded pairs of electrons, two unbonded pair, as well as two bonded pairs of electrons. So this region shows a non-symmetrical shape to a water molecule. Two bonded pairs and two non-bonded pairs create the shape of the overall molecule. And the Lewis dot theory, which really just helps us predict how the atoms bond together, will take a next step in thinking about the shape at which we're using to draw them. So as we think progressively in terms of the Lewis theory, those are the things we need to understand. That if I have regions of electron groups, we know that electrons have like charges. They're both negative. They're going to repel each other. That idea can then be extended to predict the shapes of molecules. When we say the geometric shape is the position of atoms surrounding a central atom and will be determined by the number of bonding groups and the number of non-bonding groups, knowing that we need to minimize the repulsions between non-bonding electrons. So what did I just say? Back to the water example. We need to minimize the repulsion. What possible angle can we place these electrons at to minimize how close they are together? So to minimize repulsions against like charges and to place them always back to a central atom. This theory is called the Vesper Theory. VSEPR stands for the valence shell electron pair repulsion theory, commonly referred to as Vesper. How the electron groups place themselves around the central atom to create the most stable geometric shape. And by stable, we're trying to minimize the charges of any unbonded pairs of electrons, making sure that the atoms themselves have the greatest amount of room. So what are those bond angles that create space? So that atoms, of course, take up space and shape, so we want to be sure to create a geometric arrangement and allow us to predict the shapes and the bond angles within a molecule. The valence shell electron pair repulsion theory helps us to start predicting geometric shapes. So in this slide, we're getting an idea via a picture. Suppose we have a central atom, and these electron groups are placed around the central atom. what we're showing is that electrons have repulsive forces. In other words, since this shared pair of electrons is negative and this shared pair of electrons are negative as well as the third, what possible bond angle can I place them at to create the largest space between them? And you're starting to see if I have 3 electrons pairs around the central atom, we're starting to draw a triangle. So this trigonal shape here will give us the greatest room between the electron pairs. And that's all we have to consider when we start predicting shapes of molecules. Space them out. The Lewis structure predicts the number of valence electron pairs around a central atom. Each lone pair of electrons constitutes one electron group on a central atom. Each bond constitutes one electron group on a central atom. And regardless of whether it's a single, double, or triple. So here's what we've said. If this is the central atom, nitrogen, we call these electron domains is the correct vocabulary. How many electron domains are on the central atom, nitrogen? Well, the lone pair on top of nitrogen counts as one electron group is what our text calls them. Most texts call them electron domains. That's what you'll hear me say. So the first electron domain is up north on top of the nitrogen. A second electron domain is the bond between nitrogen and oxygen. The third electron domain is between the nitrogen and oxygen to the left. It says regardless of whether it's a single, double, or triple, that creates just one domain between the nitrogen and oxygen, even though it's a double bond. Now, the information we gather from this structure, the central atom is nitrogen. There are 3 electron domains, 2 of which are bonded, 2 bonded domains, and 1 unbonded domain. The direction in which we're heading is as easy as reading a chart. 3 electron domains, 2 that are bonded, 1 that is not bonded, allows us to use the Vesper chart. And this is coming in our notes, but I'll just go ahead and kind of share it. Let me kind of blow that up a little bit so we see it clear on the screen. Again, these are all the representative shapes that our text is going to take us through one at a time, kind of explaining how these shapes form. Notice that what I'm giving you in a chart form is the electron domain geometry. Out of that, how many are bonded, how many are unbonded, and the shape of the molecule. In the previous example, we had 3 electron domains, 2 bonded, 1 unbonded. Using my chart, 3 electron domains is best described as a trigonal planar geometry. Those are the electron domains. Think about it, if there's 3 points in a triangle, those would create the largest space between those electron domains. Now, out of those 3 electron domains, 2 were bonded, 1 was unbonded. The 3 domains, 2 bonded, 1 unbonded, create what's called a bent molecule. The bent molecule places the central atom at an angle of about 104.5 degrees, and then that lone pair of electrons up on top. So if I think about